Hello! So, in this video we're going to be doing two pieces in the text we're currently using as of the time of this recording. They're actually done as two different theorems, and weirdly, the one that is essentially a lemma to prove the other one is done after the other one, which is an odd choice. So instead, I've written what is the second one in the text as a lemma, since it is proving a big chunk of the theorem. I'm going to prove the lemma first, and then I will use the lemma to prove the theorem. Both of these proofs are not very long, hopefully short enough to fit on here. If not, editing magic will ensue. And with that, I guess let's begin. So, for our lemma, we're supposing we have this function g from this interval CD to AB. It's differentiable, and we have that the derivative is Riemann integrable. In the text, they don't have this piece, but we're going to need this in order to get a little bit more to make it sort of a real useful lemma. Moreover, we're going to suppose we have this function AB, which is not an accident here, to R, and that it's continuous. So we're going to define this h of x, this function here, as just being the integral of f of t dt. I want to point out, just because notation can be a little tricky, the x is the independent variable. This is where the x is showing up. So as a function, h is taking in stuff and putting it into g to find the upper limit, meaning that nothing about what I'm putting in as x is affecting the integrand itself, okay? It's only affecting the upper limit for the integral. So we're defining h of x as this thing for obviously x where it makes sense, right? Where I could actually put in an x in the g. And our conclusion then is h is differentiable, h prime is this thing. And so again in the text, that's the end of it, is just that piece. I threw in here that g prime is Riemann integrable, so that we could also conclude as part of the lemma that h prime is Riemann integrable, and we'll see where that matters. Okay? All right, so first things first. So I've defined h of x as to be this thing, and part of this is going to be sort of important that we know that this thing makes sense. I'm going to come about it by doing sort of a whole other thing, which might seem weird at first, but hopefully it'll become clear why I'm doing that pretty quickly. So the first thing I'm going to do is define some capital F of x to be the sort of easier version of h of x. So I'm going to go from a to just x of f of t dt. So capital F of x is essentially the same idea as h of x, only the input is directly the limit of integration rather than going through yet another function g. And sort of importantly, I can note that h of x, as it was defined up here, is really just f of g of x. Okay? Because if I put in g of x as my input, g of x becomes the whole limit, and that's exactly what h is. Okay, so here, since f, where is it? F is continuous. So I'm just going to record a few things we know here. Since f is continuous, it is Riemann integrable. We know that. So I guess I should point out also that since f is Riemann integrable, this thing makes sense. But remember, I also know that if I'm taking an integral by one of those fundamental theorems, I can take the derivative. So not only is f continuous mean it's Riemann integrable, but f is differentiable. So f prime as its own thing, f prime of x, exists. Since g, so we have g is differentiable, since g is differentiable, we have indeed that f of g of x is then differentiable. So by the chain rule from derivatives, f of g of x, if I take all of this and take the derivative, I'm just going to get f prime of g of x times g prime of x. Okay? But as noted, f of g of x, right, is just h of x. So replacing this inside with h of x, I have that h prime of x, which is just f of g of x prime, is f prime, but f prime, right, if I take the integral and then take the derivative, I'm going to get the derivative of f of x minus f of a. F of a is a constant, it goes away, meaning that I'm going to get f prime of the input, g of x, times that other piece, g prime of x. So we have h prime is f, where do I want to say? Yes. Oh, and I messed that up, I'm sorry. This is what I should have written there, hopefully. Hopefully you caught that. So h prime is f prime of g times g prime. So this is the chain rules, basically what I'm saying here. So h prime is f prime of g of x times g prime of x. So I have the first thing that I want. So f of g of x, which is h, is differentiable. That was this piece. The h prime is exactly that thing. That's the second piece. Finally, I want to claim that h prime is Riemann integrable. So finally, apologies for handwriting getting a little bad at the bottom here. Finally, notice that h prime is the product of two Riemann integrable functions and thus h prime is Riemann integrable. So again, to be clear, the f prime of g of x, so we know that that is integrable, right, because we have already done the f prime bit, right? So we talked about that. Let's see. Where did we talk about that? We talked about that already. Oh, right, because f is continuous, right? So then we have that h prime is already defined, but we already had h to begin with, right? So we already have the antiderivative already exists. So h prime, yeah, is f prime of g. That's going to be differentiable because g is differentiable, and likewise g prime also is Riemann integrable. G prime also Riemann integrable, and thus h prime is the product of two Riemann integrable functions, so it is itself Riemann integrable, which is what we wanted, right? All right, so we have our lemma. All right. So now we're going to go to the theorem. So the theorem says if we have f and g defined exactly as in the lemma, meaning that g is the same domain to the same range, it's differentiable, g prime is in the Riemann integrable functions, which is what I needed here, right? That's where I used that in the lemma. We have f, which is continuous, and so we have the f and g exactly as described. But we're also adding on this little condition that a is g of c, meaning that g of c really does go to the first thing, b is g of d, so g of d goes to the last thing. I'm not supposing anything about anything in between, meaning that I'm not saying that this thing is increasing. It could go up and down and all over the place. All I know is that the first point goes to the first point, the last point goes to the last point. What happens in between is anybody's guess, okay? But knowing that, then I can make this claim, specifically taking the integral from c to d of f of g of x times g prime is the same as taking f of x, the integral between a and b. So this theorem is technically referred to and often referred to as you go further in math as the change of variables. So maybe I'll make a note of that. So this is the change of variables theorem or method. But you've already run into this quite a lot. The other thing it's known as, aka also known as, the infamous U-sub. So the U-sub here, what the U-sub part of it would be the G. It's the thing that you substitute out. You go from this F, you rewrite it as something in terms of G, which is the F of, but then you have to take the product, right, with the, whatever the U prime version is, right? So if you made ux squared, you'd have to multiply by 2x or divide by 2x to get rid of it in that case. So change of variables is really the same idea or really the same thing as a U-sub. It's just sort of the more generic version of it, okay? All right, so first thing I'm gonna do, so let me just mark these off here. So first, we apply the lemma. So applying the lemma tells me that I can get this h thing, it's differentiable, I know what its derivative is, and it is itself Riemann integrable, okay? So then, by calculation, meaning, basically this phrase is always a warning that what I'm about to write is just gonna be sort of a long string of equal algebra bits that I'm going to do to show why one thing equals another. So this is the warning, alphabet soup incoming, right? All right, so by calculation, let me make sure I'm going to start in sort of the right one, the right spot. So I want to know about C to D, right? So I want to start here, I want to conclude there. So I want C to D of f of g prime, not prime, sorry, of x, g prime of x dx. All right, so what is this? This is f of g of x, g prime of x. That is exactly h. Right? Don't tell me I messed up this lemma already. No, this was, man, I messed up the lemma. I'm sorry. This really was f. That was correct. Right, because f prime is returning the integral back to regular f. Not f prime, because h is already of the integral. I'm sorry. This really is f of g when I take the derivative. And that's good, because that's really what I want it to be over here. Whew. I might end up redoing this video as well. I'm sorry about that. For now, I'm going to push on. I may end up redoing this video later. All right, so this makes more sense now. I'm much happier. So this f of g of x, g prime of x, is h prime. C to d, h prime of x dx. But we've already concluded h prime is Riemann integrable, so I can use the fundamental theorem of calculus to tell me that this is h applied to d minus h applied to c, right? Well, what is that? So I know what h is. H is taking the input, assigning it to this top piece, okay? So I'm going to get that that equals. So I'm gonna keep this in, I wanna see if I can find, here we go. I'm gonna use this notation here, right? So I have h of d minus h of c, so I'm going to get f of g of d minus f of g of c. Okay. All right, so what is that? So here, so the reason I did this instead of jumping straight through is that g of d and g of c, these I know, right? So this is really actually f of b, because g of d is b, minus f of a, right? So that's substituting these out using the additional suppositions I made. Now I'm going to plug in what f is. So remember this f of x, right? So this is f of b, so that's a to b, f of t dt, minus integral a. So this was a because that's the definition, to b. So this is going to be a to a of f of t dt. But this is an integral of a point to itself, right? This is a zero width rectangle when I do my sum. So this thing here is 0, right? Any integral of a to a is always 0, sort of despite what's inside it, as long as what's inside it exists at that point, right? It's bounded. So this is really just then that piece, the integral a to b, f of t dt. But as we recall, that's, I mean, up to the fact that I'm using x instead of t, but that's exactly what I wanted, right? So that is the end of that. So with the, again, apology that I used f prime here when I really meant f there, because the derivative of the integral, derivative and the integral cancel out if I'm going in that direction, right? The other direction, remember, can be hairy. Trying to integrate a derivative to get back, that can be a little dodgy. But here, f, I can take the derivative of the integral of f and get back to little f, right? And now this makes more sense. This is f of g. F itself is continuous, right? G is differentiable, so it's continuous. So this whole thing is continuous. So that thing is Riemann integrable. G prime was Riemann integrable by supposition. That's why h prime is Riemann integrable. So, okay, I feel better about that now. As I said, I may redo this video at some point to make that hopefully a little more clear, but thus far, I will stop there. All right, so that's that.